Hello, welcome to Noise Management and its Control. Today is the last day of the third week of this course, and today we will close our discussion on the 1D wave equation, and specifically what we are going to discuss today is are two things. One is that we will develop some general solutions for the 1D wave equation, and next what we will do is that we will develop a physical interpretation of the parameter C. So, our 1D wave equation our 1D wave equation is second derivative, partial derivative of pressure with respect to time equals C square del 2p over del x square. So, this is for pressure, and similarly we have del 2u over del t square equals C square del 2u over del x square. So, in this class we will primarily focus on the pressure wave equation, but if we wanted to develop solutions for velocity wave equation, the theory and the process will be more or less identical. So, we do not have to worry about the velocity wave equation. So, now what we will do is that we will try to figure out a solution for this pressure wave equation. So, what we see is that this is a second order partial differential equation. So, it is a second order partial differential equation in time and x. Okay. Now, how do we develop a solution for it? So, there are several approaches you may have learnt in terms of how to solve these types of equations. One is through the method of variable separable, where you assume that pressure, which is a function of x and t, is itself made up of two functions. One is purely dependent on x. So, capital X is purely dependent on position x, and then the other thing is another function t, which is purely dependent on t. And if we use this and plug into it, then we can separate the variables and develop a solution for this. Other approach is that we can guess some solution. We can guess some solution, and if our guess is correct, then when we plug that solution back into this pressure wave equation, it should satisfy the equation. So, if we make a guess and if we plug it into the first equation, the left hand side and right side, if they are indeed equal, then we say that our guess is correct. So, that is what we will do. So, we will guess. Okay. And we will say that let us guess that p of x and t is equal to some function f1, which depends on t minus x by c. Okay. So, function f1 does not depend on t alone, it does not depend on x alone, rather it depends on a combination of t and x in such a way that we have to do t minus x over c. So, examples of such functions: what could be some examples? So, there could be infinite such functions. Some examples: one example could be a sin t minus x by c, another example could be b t minus x by c plus. So, this is another example, plus capital C times t minus x by c whole square, and I can extend this series. Another example could be an exponential thing, d e to the power of j t minus x by c. So, the point is that as long as t and x by c come in this form t minus x by c in this form, it will be a function of t minus x over c. So, we are saying that any function which is a which depends on t minus x over c is a potential solution for the pressure wave equation. So, this is our guess, and now what we will try to see is whether our guess is correct or not. So, we will rewrite the pressure wave equation. So, our pressure wave equation is del 2 p over del t square is equal to c square del 2 p over del x square. Okay. So, let us number this as equation 1, and the LHS of this equation left hand side equals del 2 f 1 divided by del t square. And the right hand side of this equation is equal to del 2 f 1 over del x square, and that equals. So, we will actually calculate the right side. So, what is del f over del x is equal to minus 1 by c times del f over del t, we can say that, or I can call it f prime. So, this is equal to f 1 prime prime. Similarly, the second derivative del 2 f over del x square is equal to minus 1 over c times minus 1 over c times f prime prime. So, this is equal to 1 over c square times f prime prime. So, what is our right side? It is c square times second derivative of f 1 with respect to x, and that equals c square into 1 by c square f prime prime. So, what we see is that left hand side is equal to the right hand side. So, what we have guessed is indeed a possible solution. It may not be the only solution, but it is indeed a possible solution for our one dimensional wave equation. So, we can conclude that P of x and t is equal to f 1 t minus x over c is indeed a possible solution for pressure wave equation in one dimension. Okay. Similarly, we can also say that P of x t equals f 2 t plus x over c is also a possible solution. Okay. So, these are the most general solutions we can think of. F 1 which depends on t minus x over c and f 2 which depends on t plus x over c. These are the most general solutions. So, in an overall sense, we can say that the most general solution for the pressure wave equation equals f 1 t minus x over c plus f 2 t plus x over c. So, this is the most general solution. we will look at a simple case, and we will initially consider only this part of the solution. Okay. So initially we will consider only, and we will see what it means, only f1 t minus x over c as solution. Then P of x t equals f1 t minus x over c. And at this point of time, what we will do is, so this is a solution for a wave which is travelling in one dimension. It is f1 represents a wave which is travelling in one dimension. f2 also represents a wave which is travelling in a single dimension, x dimension. But we will see what these two different forms mean, f1 and f2. So consider a simple tube and let us say this is my x axis and x is starting from here. So the value of x is equal to 0 at this origin, and the wave is travelling in this direction, and we say, and when we are observing the tube, we note that at time t is equal to 0, at time t is equal to 0, the pressure at the origin is, let us say, f1 of 0. Okay. At time t is equal to 0, pressure is f1 of 0. Why? Because in this, when t is equal to 0 in the brackets, this number is 0, and at origin x is also 0. So in the bracket, whatever is the only thing which is left is 0, right. So what is the pressure at origin at time t is equal to 0? f1 of 0. Okay. So at time t is equal to 0, pressure in tube at x is equal to 0 is f1 of 0. We will make a table. So we will, in this table we will have time, we will have x, we will have t minus x over c, and we will have p equals f1 t minus x over c. So we have said that at time t is equal to 0, at location x is equal to 0, t minus x over c is 0, and what is the pressure? f1 of 0. Now consider time 1 second. 1 seconds. After 1 second, we want to see where, what is the pressure, what is the pressure, and we want to find the pressure at x is equal to, so we want to find the pressure here. So at time t is equal to 1 second, we want to find the pressure here, and this distance is c meters. So what is the value of x in this case? C, right, it is c meters. And what is the value of t minus x over c? 0. And what will be the pressure? It will still be t minus x over c, which is at location 2, right. This is location 1, is f1 0. Consider time 2 seconds. At 2 seconds, we are interested in finding the pressure at location 2, location number 3. So I will call this location 1, this is location 2, location 3. I will write it here, location 1, 2, 3. So at location 3, what is the coordinate or the position? It is 2c. What is the value of t minus x over c? 0. So, what will be the pressure? F1 of t minus x over c, and this is 0. So, what this tells us is that if there was some sound present at time t is equal to 0 at origin, and if its value was f1 0, the same sound travels to location 2, which is at a distance c away from location 1 after 1 second, and the same sound travels to location 3 at time 2 seconds, right, and that location 3 is 2c distance away from the origin, which means that this sound signal which was initially at origin location 1 travels to location 2 after 1 second, and what is its speed? The distance is c, the time is 1, so its speed is c meters per second, and it travels to location 3 after 2 seconds, and again the speed is c meters per second. Okay. So, from this table we conclude that c represents speed of sound. This is one thing. C represents speed of sound, and it is for this reason, and mathematically we can calculate it as P naught gamma over rho naught, and we have to take the square root of it. So, C represents the speed of sound, and its value can be calculated like this, and if we calculate it, we find that this number is very close to the experimentally observed value of speed of sound, and because it represents the speed of sound, it indeed comes close to the theoretical value, the actual measured value of the sound speed. So, that is one. The second observation we would like to note is that f1 t minus x over c, this function, it represents a sound wave which is propagating in the positive x direction. Right. Because it is t minus x over c, it represents a sound wave which is travelling in the positive x direction. But there is no reason for sound not to travel in this direction. Okay. Sound from here, it can travel in positive x as well as negative x direction. So, the wave which is travelling in the negative x direction, we represent it as t plus x over c, f2, t plus x over c, and if we make the same table like we made for f1, we will find that for f2 also the speed of sound is same, which is c, but the direction of sound propagation is negative x direction, it is negative x direction. So, in reality, when sound travels in the positive x direction, the motion, the propagation of sound is represented by f1 t minus x over c, and in the negative x direction, the propagation of sound wave is represented by f2 t minus x over c, t plus x over c. Now, in reality, these things, these functions f1 and f2, they are important, because suppose I have a closed tube and suppose I start generating sound at the open end of the tube. What happens? Sound travels in the positive x direction, that I can represent by f1, and then it hits this wall and then it gets reflected, and the reflected sound I can represent it as by f2. Okay. So, this is the physical interpretation of f1 and f2, and the physical interpretation of c is that it indeed represents the speed of sound propagation. So, that concludes the discussion for today, and starting next week we will start solving this one dimensional wave equation for a lot of practical applications, and then after that we will start looking at noise, how it propagates, how it can be measured, how it can be managed and controlled. So, with that we close the discussion for today, and we look forward to seeing all of you on Monday of the next week. Thank you very much. Bye.